Cartesian geometry, named after René Descartes, the French mathematician philosopher who came up with the Cartesian number plane. A couple of formulas which we should be familiar with, but let's just quickly recap them. The distance formula. Now if we want to find the distance between 2 points on our number plane, there's our formula, which is basically Pythagoras' theorem. So if I want to find the distance with something. Now, some people are paranoid about substituting in the same order. In other words, if I use 5, then I must use 3 first in the other one. It's probably not a bad idea, but for this it doesn't actually matter because you're going to square it anyway. If you sub in the other way around, it just becomes a negative number and you square it, it's positive. So you could do it the other way around and that's fine. As long as you match an x with an x and a y with a y, you'll be okay. 5 minus 3, 3 minus minus 1, we get our answer, and simplifying it down we get 2 root 5. As I say, it's basically Pythagoras' theorem. What we're doing is we're joining 2 points up, creating a hypotenuse of a right angled triangle, the 2 sides of the triangle being the difference in the x and the y values. The midpoint formula, there it is, our wonderful midpoint formula. So if we wanted to find the midpoint, and again it really doesn't matter as long as we match the x's with the x and the y's with the y's, because when we're adding, well, the order of adding doesn't matter. There we go, 3 minus 2 over 2, 4 plus 1 over 2, and there's our midpoint, which is basically finding the average of 2 points. Right? The middle is the average when you're talking about 2 things. Now, using Euclidean geometry with Cartesian geometry. They're both geometry, it's all geometry. Euclid, of course, came up with the idea of Euclidean geometry. As I say, Descartes came up with the idea of Cartesian geometry. And of course, maths was done with Euclidean geometry way before it was done with Cartesian geometry, because maths was all done with geometry before we knew about algebra and things like that. So often the ideas from Euclidean geometry can help us in other geometries, and it can save time. So as a reminder, let's have a look at our quadrilaterals and classifying them according to features they possess. There's the family tree for quadrilaterals. And as I said there, as you branch down, go further in the tree, that quadrilateral, sometimes it will have their own features, so it becomes more specialized, but it will also possess any feature of the shape that it came from. Now, for instance, a rhombus. There's a rhombus over here. It will have the properties, the specific properties of a rhombus, but it also will have any properties of a parallelogram, a trapezium, a kite, and a quadrilateral in general. So let's list the features as we branch down. A quadrilateral, there's not a heck of a lot we know about quadrilaterals other than, oh, it's got 4 sides. How useful is that? And oh, it's got 4 angles as well. But yeah, other than that, there really is no specific properties that we can use with a quadrilateral. But as we branch down, let's go over to the kite. The kite is the one where we have a pair of adjacent sides. That's where adjacent sides are equal. But it also turns out the diagonals in a kite are perpendicular as well. And you can prove all that with congruence. The formula for the area of a kite, which often is misstated as the formula for the area of a rhombus. And it's not actually the formula for the area of a rhombus, it's the formula for the area of a kite. So that's half xy, where x and y are the length of the diagonals. Over the other side, we branch to the trapezium. It has 1 pair of parallel sides. And we have our area formula for a trapezium, half the perpendicular height. A plus B, and A and B are those parallel sides. Well, from the trapezium we go down to our parallelogram. Now that means you could, if you wanted to, use the trapezium formula to find the area of a parallelogram. But it now has 2 pairs of parallel sides. What do we know? Well, because it's a parallelogram, opposite sides in a parallelogram will be equal. It's also true that the opposite angles in a parallelogram are equal. Diagonals in a parallelogram will bisect each other. And the area is simply base times height, where height is the perpendicular height. Now, if you wanted to prove something was a parallelogram, actually, you can do it with just 1 pair of sides. If they're both parallel and equal, then that's enough to say it's a parallelogram. So we have the kite, we have the parallelogram. The parallelogram goes over to the rectangle. Comes a little bit more specific. Angles in a rectangle we now know are 90 degrees. When it comes to the diagonals in a rectangle will now be equal in length. And the formula well, we say length times breadth. And if you think about it, that actually is the same formula for the parallelogram, because base times perpendicular height, well, the perpendicular height in the rectangle becomes the length or the breadth, depending on how you're looking at the shape. Our rhombus branches off, but now we know the diagonals in a rhombus, they will bisect the vertex, and you'll notice I haven't put an area formula there. And that's because the rhombus is a kite. So we can use the formula for a kite. And that's why it's often missaid that the formula for a rhombus is a half xy. Well, I suppose it is, but it is because a rhombus is a kite. I mean, you could just as easily use the formula for a parallelogram to find the area of a rhombus. We get a little bit more specialised. The square, which is both a rectangle and a rhombus, so it has all those features. Really, the only extra thing we could add, sounds silly, well, we could get a more specific formula for the area. It'll just be the side squared. Maybe that's why we call it a square. Which word came first? Was it the shape or was it the square? What came first? Something like this. Here we go. We've got 4 points there. Creates a quadrilateral. We want to show that actually this is a rhombus. Different ways I could do it. I decided to play with the midpoints. So I found the midpoint of AC, turned out to be 5 on 2 minus a half. I found the midpoint of BD. Oh look, they're the same thing. Well, if their midpoints are the same, then I know it's a parallelogram because the diagonals are bisecting each other. So at this stage I can't call it a rhombus, but I can call it a parallelogram. We need to get a little bit more specific. So now I'm going to find the length of some sides. If I find the length of CD, it turns out to be 5, and the length of AD also turns out to be 5. So now I know it's a rhombus because I've got a parallelogram, but I've now also shown that the adjacent sides are equal. Now I didn't have to show both pairs the adjacent sides were equal. That could have been one way I could have done it to find a rhombus, because I've already shown that it is a parallelogram. So a parallelogram, it also has adjacent sides equal, got to be a rhombus. So it's that sort of idea. Okay, that should do so.